Okay, getting started here. We're going to continue in our discussion of optics. And I have just 3 or 4 slides here. Okay, maybe it's 5. That is material that I talked about on Friday. I went kind of fast on Friday and I didn't spend any time on the equations that go with the things I talked about. Yeah. You will need a total of 2 between now and the end of the semester. Yeah, that'll cover it. Okay, so then we're going to get to talking about reflections. We won't get to refraction in class today, but we will for lab today. So first, this Young's double slit experiment. Young's double slit experiment had, as was correctly identified by at least one person on a potential test question, a very important effect on physics in that it showed that light has to have a wave behavior, that you can only explain this behavior if light behaves as a wave. Why? Because when I have light, now this picture shows, see those 3 parallel lines down at the bottom? We call those wave fronts. The light itself is coming like this. And so the wave fronts are showing us the locations where my waves are at the peak in their amplitude. Remember, the wave is traveling and doing something like that, right? And the wave fronts are drawn, so here's one wave front, here's another wave front, here's another wave front. So the wave is traveling in that direction, and those wave fronts are where the peaks are as it's traveling. So does the wavefront picture make sense to people? Is it clear what it's specifying? A key aspect of that is when the light gets to these slits, it's in phase. That is, the wave is at a peak here and at a peak there. And when it goes through those slits, a principle that has been studied and found to be reliable is Huygens principle. That says every point on a wavefront can be treated as a point source for a new wave. Now, point source. Let's just think about a simple point source. I drop a pebble in water, and it is a point source for waves. What direction do the waves go from the point where the pebble hit the water? Outward. They go out as circular waves on water. Now, if we're talking about a light wave, so that's like we have you have a cigarette lighter, and you flick your Bic. What direction does the light go out when the flame starts up? It goes out in all directions, so it's a spherical wave. That is, if you were to look at where the wave fronts are, those wave fronts would be forming spherical shells. And so Huygens' principle says I can treat each point on a wavefront. So for instance, I could treat this point and this point and this point and this point and all those points as if they are little points where a light was started. And so the light comes out as a spherical wave from there. Of course, drawing on my tablet, that comes out looking circular because it's like dropping the pebble in the water. It's just 2-dimensional surface. And hence you have circles are what you see in the 2-dimensional drawing. So the light from each one of these places can be treated as if it comes out as a spherical wave, and then you add up all of the different spherical waves, and when you add them all up, it adds up to give you another straight line if you started with a straight line. And so using Huygens' principle, you can predict that these wave fronts are going to progress as shown. Well, what about when it goes through the slits? Now I'm treating each place where there's an opening in the slit as a point source, and the light's going out in spherical waves. And so that means the light that goes through this little slit is going to go out in all directions. It's not just going straight through. It goes out in all directions. We call that diffraction, light bending around a corner. So let me get that word up here. It doesn't only work for light, it works for any wave. So it's a wave bending around a corner. We know that happens with sound waves. If we had perfectly soundproof walls and I stood out in the hall and I said something with the door open, it would bend around and you'd be able to hear it. We're all very familiar with that aspect. We aren't so familiar with it with light, because if I stood outside not in a straight line from you to me through the door, you wouldn't see me. But light does bend around corners. It's just the intensity is much weaker for the bent waves. This example here with two little slits, the light bending is pretty much all you see. Now you do see some straightforward. When you wore those little glasses Friday and you looked at the lights, you did see the lights, right? That was the strongest. But you had really strong light bending off in different directions, diffracting. Well, because I have two slits, I'm going to have different path lengths. So let me just choose a location, and I will happen to choose this location here. And if I draw a line from the center of each slit to that location, those lines aren't the same length. They're different lengths. If the light was in phase when it came through the slits, but it had to go longer from one slit to my screen than it went from the other slit to the screen, what is that going to tell you about the phase between the light when it hits the screen? It's going to be off. And the amount it's off depends on the difference in the two path lengths. And so from doing what we call the Fraunhofer or far field approximation, saying that the distance capital D here is very large. Okay, the distance capital D here, the distance between my slits and the screen, is very large compared to the distance between these two slits here, which we usually use a lowercase d for. In that case, then it turns out that my path length difference, my path length difference is equal to the separation in the slits times sine of theta, where theta, I should have drawn it to, I'm going to erase these lines and draw them to the ones that it shows for the angle theta. Shows the angle theta to there. So you can see where the angle theta is defined. Does everybody see where the angle theta is defined? It might be hard to see. Hi, Daisy. Here is theta, and it's going out to this black line. So I'm going to redraw that black line darker. Actually, I'll draw both the black lines darker so you can see them more clearly. So there's the definition of the angle theta. And a big theta. There, big theta. So the path length difference is d sine theta. Now we learned about constructive and destructive interference. How much should the path length vary if I'm going to have constructive interference? Anyone? What condition gave us constructive interference? When they're in phase. So what's the smallest path length difference for them to be in phase? you say it, Andrew. Okay, thinking. Why are these two rays going to be out of phase? And so, what length difference would make them in phase? Exact same. If they were the exact same lengths, they would still be in phase. So the smallest difference in length would be 0. That would be in phase. But how long does a wave travel before it repeats? What do we call that? A what? As you said? A wavelength. If a wave travels a wavelength, it will be back to the same phase. And so we could also be plus or minus for the difference, 1 wavelength, or we could be plus or minus 2 wavelengths, etc. So we write this condition as delta L is equal to m lambda, where m is any integer. Now, what about destructive interference? What condition led to destructive interference? If they were what?
Out of phase.
Out of phase by how much? You could say lots of words for that. Opposite. Okay, opposite works. So there are many words. Opposite, that means when one is at its peak, the other is at its minimum. Well, in a wave, how far do you have to go through the wave for it to go from peak to minimum? Half a wavelength. So if delta L is 1/2 wavelength, and we could put plus or minus a half wavelength, or if we shift by another wavelength, we're going to be back to the same situation, so we could have had plus or minus 3/2 wavelength, etc. So we write this as delta L is equal to m plus 1/2 lambda, where m is again any integer. So taking these, I can now write equations for destructive interference. I have from our work up here, well, I didn't do the work, delta L is d sine theta. So d sine theta is equal to m plus 1/2 lambda for destructive interference. And for constructive interference, d sine theta is equal to m lambda. So I have these two conditions that will give me where constructive and destructive interference occur. Now you might wonder, okay, I talked about this on Friday and just didn't do it with the equations. Why am I spending the time today to do it with the equations? I already have the homework assignment, the last homework assignment up for you on Moodle, and you need this to be able to do that homework assignment. So those are our angular conditions for constructive and destructive interference. I'm going to have a clicker question here, so I'm going to make sure I am ready for the clicker question. Here is where the geometry is actually shown. If you're far enough away, you can treat this triangle as the ever common 0, 90, 90 triangle. It's not actually 0, 90, 90, but this angle alpha is very small if we're in the far field, if this capital D is much, much greater than lowercase d, then the apex angle alpha is approximately 0. It's very, very small, which makes the other two angles add up to 180 degrees. And we square it off. We find the difference just by looking at this triangle right here. The opposite side is the hypotenuse times sine of the angle theta. That's where the delta L equation came from. And so here is putting together the equations that we already derived for constructive and destructive interference. What causes the constructive interference? What causes this to be constructive? That's the words I was looking for. And this one here is destructive. What causes it to be destructive? Out of phase. So we're able to derive these equations by using geometry and the definitions for constructive interference when it's in phase, destructive interference when it's out of phase. Now the clicker question. A laser is used to illuminate two narrow parallel slits. The interference pattern is observed on a distant screen. What happens to the pattern observed if the distance between the slits is slowly decreased? I'll rewrite the equation for you. There's the equation for constructive interference. Okay. 3, 1, and 4. Okay, turn to your partners in discussion. I just say 2 groups of 4 in this case. And discuss what you answered and why you answered it. See if you can figure out the correct answer. Okay, let's work now as a single group. I've heard different ideas from people. Start with the most important part here. We want to look at the pattern observed. And so the pattern observed, what is going to define the size of the pattern observed? Well, that's going to affect it. But when I'm looking at the pattern, which one of these variables is telling me what the pattern is specifically? Right, I have d, theta, m, lambda. Which one's telling me specifically what the pattern is? I'm going to go back to picture one more. Which parameter is going to describe this pattern? So this pattern, here's the pattern, right? Which variable tells me about that pattern? What did you say, sir? Sarah, wow. Rachel? Theta. Theta is the correct answer. Theta is telling me the angle where I'm going to see constructive and destructive interference, depending on which equation you're looking at. So theta is the important thing we want to consider. Now, one more, come on. I think this is the right slide. So we look at this, we want to find what's going to happen to theta. So I'm going to actually solve this for theta so that we can focus on that variable. I'll start with sine theta is equal to m lambda divided by d. Theta, for small angles, theta is proportional to sine theta. So we'll just stick with the small angles and we'll be good, just saying what's going to happen to sine theta as d gets smaller. That's what the question was really asking. Right? This is, part of physics here is taking the words of a word problem and translating them into what is it really asking. And then we have to look at equations and say how the equations relate to this. So as D gets bigger, distance between the slits, gets smaller, excuse me. D gets smaller. As D gets smaller, what's going to happen to sine theta? It's going to increase. Well, sine theta is telling me where my bright fringes are. And so if the angle between them increases, what's that going to do to the spacings? It's going to increase. So now let's ask the question again. You still have an answer, Tyler. Okay. Repolling, we had 7, 0, 1. Well, like we said, if D decreases, then theta must increase. And so the correct answer was A. All right, now on to the equation for polarization. We talked about polarization. Was polarization something that had to do with waves? Yes, it was. At this point, everything we're saying has to do with waves. We won't get to looking at light as a particle, but light has a dual nature, both a wave nature and a particle nature. More specifically, what kind of waves can experience polarization? It's what? Well, electromagnetic can, but we had basic categories of waves. We had longitudinal waves, transverse waves, and then we had the combination waves like Rayleigh waves and Love waves. So, which type can experience polarization? It has to be transverse. It has to be a wave where the displacement is perpendicular to the velocity, because polarization has to do with the perpendicular direction from velocity that the waves are actually oscillating in. So this is a function of specifically transverse waves. Not any wave, but transverse waves. So this picture actually shows you a polarizer made for radio waves. So we have radio waves. We have an antenna. It's kind of hard to see there in that picture. Actually, this will make it probably even harder to see. The antenna goes out to the left and to the right, or right and left. I don't know which order I did them. And so we're going to have electric fields in the horizontal direction. Now remember I said when we're talking about polarization or electromagnetic waves in general, we can either talk about the electric fields or the magnetic fields. We can talk about either one. It's up to us. But we choose one and we go with it. So if I have electric fields, I put this piece of metal. This is a piece of metal that conducts electricity. If I have an electric field like this, what's going to happen in the metal when that electric field hits it? What does an electric field do to charge? The whole purpose of electric fields, in fact. Anybody remember the definition of an electric field? Those 3 lines means is defined as. Okay, the definition is the electric force divided by charge. The whole purpose of electric fields was to allow us to easily find the force if I put some random charge in there in an electric field. So if I have an electric field that gets to that surface, there's going to be a force on any movable charge equal to the charge multiplied by the electric field. So it's a conductor, there's a force on the charge, and what's special about conductors compared to insulators? The what? They allow the electrons to move. So I have electrons there, there's going to be a force on them because of the electric field, and they can move because of that, so they're going to be accelerated. Well, if I have a charge and I have a force on it, and it moves parallel to that force, what is that? Force times distance, what do we call that? Force times distance parallel, I have to be careful. Work. If it was force times distance perpendicular, it would have been torque. But force times distance parallel is work. So the electric field is going to do work on the electrons and make them move side to side. Well, if you make the electrons move side to side, you did work. That means you took energy from the electric field and put it into the motion of those electrons. What does that mean? That means you absorb the energy. So when my waves hit where I've shown the blue line, the energy will be absorbed because the electrons can move that direction. But what if I go up higher, here? Because of those slits, the electrons can't move horizontally there. Because they can't move horizontally there, they can't absorb the energy. And so the wave goes through. So this will allow the wave to go through because it can't absorb electrons with horizontal motion. It can absorb vertical motion. So if I had vertical electric fields, it would have allowed it through. So here we just rotate 90 degrees. Now I have my electrons can easily move like that between the slits, and so it can absorb, and so that doesn't allow the light through. So that's how we make a polarizer. That's how we make light polarizers too. Remember those sheets I had? Those sheets, this was a process developed by, was it Edward Land, the guy who invented the Polaroid camera? Polaroid because he used polarization as part of the process. He took polymers and he stretched the polymers. And when he stretched it, it formed little cracks like this. And then he put in those cracks molecules that had an electric dipole, which would then allow you to have, parallel to those slits, you could absorb electric fields and make the dipoles oscillate. Perpendicular to those slits, you couldn't. And so it's exactly the same thing. Now, this last picture is showing at an angle. This will allow electric fields in this direction to transmit, and this direction they're absorbed. And so we have horizontal electric fields coming, and in one direction it'll absorb, one direction it will transmit. And it turns out that the amount that is horizontal is allowed through of electric field. In terms of intensity, we get the law of Malus. I'm going to go to the next slide on. The law, nope, not the next slide on. I guess I took it out. The law of Malus is shown up here. I'll write it bigger. The intensity that goes through a polarizer is equal to the intensity on one side, the intensity that hit it, times, that's not a C at all, cosine squared of the angle between the original polarization direction and the transmission axis. So if that angle is 0, cosine of 0 is 1 and allows everything through. So in this case here, theta was 0. Cosine squared of theta is equal to 1 and allows everything through. In this case here, theta is 90 degrees because the transmission axis is vertical. The electric field is horizontal, so cosine squared of theta is equal to 0 in this case. So when I was rotating the polarizers, the intensity coming through, if they were perfect polarizers, would follow this equation, the law of Malus. That's how we spell Malus. It's a dude's name. It's not talking about his personality flaws. What if I had unpolarized light going through a polarizer? This all dealt with polarized light. What if it was unpolarized light? Yeah, it allowed the part of the unpolarized light that's parallel to its transmission axis through and block the others. On average, that's half. So if I just have light and it goes through my polarizer, half gets through if it was unpolarized. So if you're wearing polarized sunglasses, the polarizer will cut out half of the light. So it will be darker. But then if you have polarized light, you'll cut out none or all or somewhere in between depending on the angle. Here's an application. Liquid crystal displays. Anybody have a liquid crystal display nearby? Yes, you do.
I do.
You have a clicker, you have a cell phone. Both of those are using liquid crystal displays. Where they're very, very common. The liquid crystal display works because there are liquid crystals that you put a voltage difference across them, and it will rotate the polarization direction. Just like, remember, I had that tape that rotated the polarization direction, and by making it thicker, we had different colors that were rotated so that they would be transmitted. That's essentially what's going on with your LCD display, except for it's voltage controlled. And so in your LCD display, you have a front polarizer, and then you have a liquid crystal that will rotate the polarization depending on the voltage on it. And then you get to a second polarizer, and depending on how much you rotate it, you could have blocked it or you could have allowed it through. And so it just depends on the voltage and the orientation of your polarizer, what's going to happen. So if you, for instance, had, let's say it was a calculator, and it has a square window, you could pop the front window out, which has the polarizer in it, rotate 90 degrees and put it back in, and it will change it to a reverse field. What was black becomes light, and what was light becomes black. Which is kind of cool. Actually, there are different ways. Some of them use a backlight, and some of them just require room light. If it's just room light, it's that same polarizer is the front and rear polarizer, and it doesn't work. If it's backlight, then it works. Don't break your calculator. If you have a cheap calculator that you don't care about. Okay, this is my last slide on polarization things. I talked about me being goofy wearing polarized sunglasses and looking at the road going like this. Or I go to the beach near sunset, got my polarized sunglasses on, I look out over the water because, of course, in California, sunset is over the water. And go like this, and look, like this. I don't see the glare of the sun on the ocean. Like this, I do. It's really cool. I mean, anyone should be able to enjoy that. Well, the sky is also polarized. I especially noticed this one summer. I was working up at Fossil Butte in Wyoming, pretty high elevation. And wearing my polarized glasses, looking up the sky, I could really change the sky's hue by rotating my head. Why? Because that Rayleigh scattering that makes the sky blue occurs with sunlight being, coming to a molecule, and then the molecule will oscillate with whatever direction the electric field was. And then it will re-emit light, but the re-emitted light has to be perpendicular to the direction that the electric field was oscillating. So if I have sunlight and it comes to this particle here, if the light goes forward, it can still be polarized in any direction. But if I'm at a 90-degree angle, it has to be completely polarized. because I have to have this direction is perpendicular to the polarization direction, or to the direction of the electric field oscillation, but it also was perpendicular to this direction. So being perpendicular to both of those only allows light in one direction. So if you look at the right angle, so you're looking to a height in the sky where the light coming from the sun hits there and then comes to you that's a 90-degree angle, it'll be perfectly polarized. I believe I saw this a lot more in Wyoming than I tend to down here, because in Wyoming I was up there at pretty high elevation and there was less air above me, which meant that I had less variation in the heights where the Rayleigh scattering was occurring. And so it was, more, this is all closer to 90 degrees and I'd see more cut out. It's kind of cool, isn't it? You guys need to be as completely excited about this physics stuff as I am. Okay, now we're going to shift to talking about mirrors and forming images. So we're going to be using what we call geometric optics. That means we're going to use our geometry skills, and we're going to treat light as rays. If I say light is a ray, some of you from your geometry should remember what a ray is. Now that I say some of you should, is there anyone who can volunteer what a ray is? Okay, that's perfect. A ray has a starting point, no ending point. The ray model for light, and it travels in a straight path. The ray model for light is just that. You have a light source. That light source has a specific starting point. Goes in a straight line forever, unless we worry about it hitting something or the warping the space-time continuum caused by massive objects. We're not going to worry about the warping the space-time continuum caused by massive objects. And so we're going to say that that light's going to travel in a straight path forever unless it hits an object. That's what ray optics is about. And so we're using geometry with that straight line optics. So, first just looking at what's happening with light. We've already talked some about reflection. We talked about specular reflection versus diffuse reflection. Light from this light bulb hits the gentleman's forehead and nose. What kind of reflection is he having? Is occurring when the light reflects off of him? Specular or diffuse? It's diffuse. It's diffuse because it's spread out. So if I look in his forehead, I don't see my reflection because the light's all spread out. Right? That's what the diffuse means. So if I were to look at him, I wouldn't see my reflection in his forehead. Now this here is just going back to the whole wavefront idea. I'm not going to spend any more time on that because I already talked about it. And go to what happens when light hits a mirror. Picture here when light hits a mirror. You had the wavefronts coming in, reflecting and coming out. And our first law about reflections is that if we have a specular reflection, the angle of incidence equals the angle of reflection. This is sometimes called, I think it's the law of reflections or something like that. What does the word incidence mean? Right? When I took this class, it wasn't clear to me. And then it makes this whole equation not so useful if it's not clear what the angle of incidence means. So what does the word incidence mean? Any ideas at all? It is very good then that I'm bringing this out. Incidence, the angle of incidence is the angle of the light coming in. So the angle of incidence is the incoming light, the angle that's coming in. Reflection is going to be the light that reflected and is leaving. So this is the going out. When we measure these angles, probably the most important thing in all of what you do with mirrors is that you're measuring the angle of incidence and the angle of reflection from the surface normal. Now, we've talked about normal since the beginning of the semester. We talked about the normal force, for instance. If I have my tablet sitting on this desktop, there's a normal force. What direction is that normal force pointing? Okay? It's a three-dimensional version of perpendicular. And so the normal direction is coming directly out of the surface. And that's the direction of the normal force. That's why we call it the normal force. It is not the common, normal common. It's not that. It's the direction normal. So we measure our angles from the surface normal. That is the direction coming, the three-dimensional equivalent of perpendicular from the surface. So in our pictures, it's always drawn as a perpendicular to the surface because you have a one-dimensional line for the surface. So the angle of incidence is going to be this angle right here between the incoming light ray and the surface normal. What's the common mistake that people would make? Yeah, the common mistake people would make would be to measure this angle. When you're doing reflections, as long as you stay on the plane of this and this, of the incident reflected, that would still work. But when we get to refraction, we use the same definitions and it won't work. So for whoops, that would be not what I wanted to do. For reflections, it doesn't really matter, but for refraction it does, so we do the same thing to make sure we do it right every time, instead of changing the rule from one case to the next. So there's our angle of incidence that I marked in blue. The angle of reflection is there marked in green, which was a poor choice of colors, because I had the wavefronts in green as well. There's magenta for the angle of reflection. And our law of reflection says that those two angles have to be equal. It's a simple rule. It's the same as if you were to bounce a ball off of a wall or off of a table and there was no friction involved. There you go. There's the law of reflection. Angle of incidence has to be angle of reflection. Let me, before I go to that, I'll go to that just at the end of time. If you're looking in a mirror, you have light that comes from whatever room light you have. It hits your nose in this case, reflects off of your nose how? What kind of reflection? It's a diffuse, because it reflects in all directions. So I have light from the nose is going off in all directions. And then it hits the mirror, and everywhere where it hits the mirror, it's going to reflect according to that law of reflections. Now, when I look into the mirror, my eyeball is somewhere back here. My eyeball sees these two rays, right? This ray here. Okay, change color. This ray here, and I tried to make it so this ray here make it into my eyeball. And my eyeball says, I'm seeing something, and it just extrapolates back. And so we extrapolate back, and it says, those two met back here. So my eyeball doesn't register there's a mirror, my brain may, but my eyeball doesn't. My eyeball simply says they met back there. And so my eyeball says that I'm looking at my nose at this position. So let me call this D, the distance from my eyeball to the, actually, that's not what I want to do. I want to call this distance here D. The distance from my nose to the mirror. Just using geometry, because this angle is the same as this angle, that means it's also the same as this angle. And so I have these dashed rays are doing the same as the rays that were coming off of the nose. And thus, just by symmetry, this has to be the same distance. So when I look into the mirror, I'm going to see the image of the nose behind the mirror, the same distance behind the mirror as the nose was in front of the mirror. We have names for these kinds of things. I thought that was my next slide, but apparently not. My next slide must be. Okay, you can answer now. It wasn't available when I started. How tall must a plane mirror be in order for you to view your full height reflected in it? So this is an experience question, not one we've talked about. You want to see your whole body in a wall mirror. So the wall mirror is parallel to you. It's vertical. How much mirror do I need in height to see my entire body height? Okay, we had quite a few people who changed their answers. They thought about this. The slight plurality was a little taller than your height. We had equal on half your height and 3/4 your height, and one exactly your height. Well, let's look at this, right? This was not one that you were supposed to know the answer. This was just gauging what it feels like to you. So here should be a picture of a gentleman looking at himself in a mirror. He's a gentleman because he's wearing nicer clothes than I ever wear. Light from his feet come up, hit the mirror, come back to his eyes. Light from the top of his head comes down, hits the mirror, comes back to his eyes. Using the same geometry that we just looked at, if I draw these normals, theta incident for the foot, theta reflected for the foot, how do those two angles compare? They must be equal. So since those are equal, then that means this angle here is the same as that angle. The theta incident foot is the same as theta reflected foot. And that's opposite to this, so it's the same. And so that means I have identical triangles here and here, right? And then I have the same thing going on for the eyes. I usually do this just saying the eyes are at the top of the head, so I only have to have one triangle. If these are identical triangles, how does the center height compare to the full height from the feet to the eyes? It's got to be half. And likewise, for up here, it would be half going out to the normal. So that means when you put it all together, that wall mirror only has to be this distance here, which is 1/2 of his height. So you only actually need a mirror of 1/2 your height to see your entire body. But of course, it has to be mounted correctly. You need to have the top of it at the height that's halfway between the top of your head and your eyeballs. The bottom of it at the height that's halfway between your eyeballs and your feet. Now, when they put a wall mirror up, they don't know who's going to be looking in the mirror, right? And so they put the bottom so it should be a little bit below, halfway high for anyone that's going to use it. So assuming you're going to have somebody who's like 4 feet tall, a kid looking in there, well, you'd want it to be down to 2 feet for them to be able to see their feet. Assuming you have a full-grown man, somebody who's 6'6", then you'd want the top to be somewhere around his full height, so around 6'6". Is that what they do? No, because they don't consider full-grown men. They consider average men. And so they make the tops of those things somewhere around 6 feet. Which means when I'm looking, my eyes are right about 6 feet. I'm looking pretty close to the top, and I don't see anything up above. It's even worse when you get to a bathroom mirror. I'm sure even people who are, half a foot shorter than me experience problems here. You want to look in that mirror and you want to shave, right? But in order to shave, you have to see your face if you're going to try to, aim your strokes. And they mount those things so they're like here. So I look in the mirror and I can totally see my collarbone. Doesn't help for the shaving. So what does the full-grown adult have to do, Zach? Yeah. Until you get old and you discover that hurts your back. So this is what I do to shave. I spread my legs out so I can get down lower and see myself. Because nobody builds things. And I mean, I wish that I was taller. I think a lot of people have that same wish. I'm not exceptionally tall, but still annoyance. So if you ever get into designing homes, just think about that. Not everybody's 5'9". All right, we're out of time. I don't get to show my display stuff, but we'll have another lecture. We'll continue actually with this for lab today.